All right, next what I want to do is I'm going to talk about the ratio and the root test, and these are very, very similar. And the way that I want to motivate these, let's talk about the ratio test first. The way I want to motivate these is by thinking about geometric series, because essentially the ratio test is going to take an arbitrary series and compare it to a geometric series. And so just remember what we know about geometric series. If we take x to the n as it goes from 0 to infinity, this converges. So this converges if the absolute value of x is less than 1. And in fact, we know what it converges to, but that part we don't care. All I want to focus on today is that it just converges if the absolute value of x is less than 1. And so what this means is if you think about kind of the sequence a sub n being x to the n, as n goes from 0 to infinity, so this is just 1x, x squared, and so on. And if you were to look at the ratio a sub n plus 1 over a sub n, think about what's going to happen here. A sub n plus 1 is going to be x to the n plus 1. A sub n is x to the n. And therefore, the ratio of those consecutive terms is going to be x. And so what this tells you is that the series converges. So the series converges. We know it converges if the absolute value of x is less than 1. And actually, what I want to do is not just look at the ratio of the corresponding sequence or the consecutive terms in the sequence, but the absolute values of those. Okay, and so if that's less than 1, we know that we get a convergent series. Okay, and so what we can do, it turns out, is start with an arbitrary series, look at this quantity as n goes to infinity, and that'll tell us whether the series converges or diverges. And that's called the ratio test. Okay, so here's what the ratio test says. Consider the series a sub n as n goes from 0 to infinity or 1 to infinity or whatever you want. Okay, so consider that series. Then this series will converge. So this will converge absolutely if the limit of a sub n plus 1 over a sub n as n goes to infinity, if that limit is less than 1, we get absolute convergence. The series will diverge if that limit as n goes to infinity of a sub n plus 1 over a sub n is bigger than 1, and the test is inconclusive otherwise. So the test actually doesn't work. Well, it doesn't tell us what's going to happen. It still works. It just doesn't tell us anything if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is 1. Okay, so the test is inconclusive there. Okay, and so let's think about some of the series that we've worked with and think about how the ratio test can be useful here. So one of the series that we worked with last time, so one of the series that we worked with in class is the sum of 1 over n factorial. And basically, whenever you have a factorial in your series, the ratio test is almost by far the best way to go. Okay, so if you have a factorial in your series, the ratio test is almost always the best way to go. And so let's look at, our sequence that we're looking at here is 1 over n factorial. And so let's compute this value. By the way, this limit of the absolute value of a sub n plus 1 over a sub n, typically we call that L. Okay, so we're going to compute L, which is the limit as n goes to infinity of a sub n plus 1 over a sub n. And what I want to do is I want to think about, we already know what a sub n is. a sub n is going to be 1 over n factorial. A sub n plus 1, we're going to go to the same sequence and replace all the n's with n plus 1. So this is going to be 1 over n plus 1 factorial. And we take absolute values. And then if we're dividing by 1 over n factorial, that's the same as multiplying by n factorial. So this is going to be n factorial over n plus 1 factorial. And factorials are always positive. And so we can actually just drop the absolute value. We don't really need that. We have n factorial over n plus 1 factorial. And then finally, this is reduced to a limit problem. So if we take n factorial over n plus 1 factorial, everything's going to cancel except for the n plus 1 term in the denominator. And as n goes to infinity, this limit is going to be 0. And therefore, since the limit is less than 1, we see that this series converges absolutely. Okay, so the series 1 over n factorial, as n goes from 0 to infinity, converges absolutely. Because this is a sum of positive terms, there was no chance that it could converge conditionally. So the only choices were absolute convergence or divergence. But it turns out since it converges, it must converge absolutely. Okay, so that's the ratio test. And I want to point out that when I say that the test is inconclusive, I should have spent a little bit more time on this when I said it, but let's do it now. When I say that the test is inconclusive if the limit's 1, what I mean is that there are examples of series where this limit is 1 and the series diverges. There are examples of series where this limit is 1 and the series converges absolutely. And there's series where this limit is 1 and the series converges conditionally. All of those things can happen if the limit is 1. So knowing that that limit is 1 just doesn't tell you what happens. You have to do some more digging. You have to do either the alternating series test or maybe just you have to take the absolute values of the terms and look at whether it converges conditionally or converges absolutely, just like we were doing before when we were looking at these definitions. Okay, so the test just doesn't work there. One other place where the test doesn't work, and this actually, you can take this next example and you can basically build examples where the test fails and the series will do whatever you want it to do. It turns out that the ratio test is always going to fail when you have rational functions. And by rational functions, what I mean is ratios of polynomials. And so if you were to have something like n squared plus 1, let's make it alternating so that there's at least a chance it could converge conditionally. Let's say a negative 1 to the n times n squared plus 1 times, let's say, n to the 4th plus 2n plus 3 as n goes from 0 to infinity. Now, what I want to do is I want to take this series, I'm going to call this a sub n, and I'm going to compute that limit L. And this is not going to be as bad as you think it is because of the way that I've taught you how to evaluate limits. So a sub n here is negative 1 to the n times n squared plus 1 over n to the 4th plus 2n plus 3. Okay, and therefore L, so this is a new example, so L is going to be the limit as n goes to infinity of a sub n plus 1. So I'm going to take the absolute value. We're going to look at a sub n plus 1, so that's negative 1 to the n plus 1 times n plus 1 squared plus 1 over n plus 1 to the 4th plus 2 times n plus 1 plus 3. So that's our a sub n plus 1. And then we're going to divide that by a sub n, which is negative 1 to the n squared plus 1, all over n to the 4th plus 2n plus 3. Now, this looks like a mess. And it kind of is, but it kind of isn't. And I'll show you a nice way to evaluate these limits when you have rational functions. First of all, we can drop the powers of -1 because we're taking absolute values. The absolute value of -1 is 1, and 1 to any power is 1. So we can just drop the -1 to the ends. And we can also drop the absolute values after that. And so if we ignore those, and then we think about this bottom part and we're dividing by a fraction, we're multiplying by its reciprocal. So this is going to be n plus 1 squared plus 1 over n plus 1 to the 4th plus 2 times n plus 1 plus 3 times the reciprocal of the denominator. So that was n to the 4th plus 2n plus 3 over n squared plus 1. Now, what I like to do, and maybe you can see it right away here, but just to make this super obvious, and I'm just totally cheating with the iPad here, I'm going to rearrange this product. We're multiplying things here. So we're multiplying, and that means that the order that we're multiplying doesn't matter. I'm totally cheating here. But I'm going to switch the numerators. And notice that if I switch the numerators, I'm not actually changing the product, I'm just rewriting it. But the reason why I want to switch the numerators is think about what each of these fractions is going to be. This is a 4th degree polynomial over a 4th degree polynomial. So you have n to the 4th plus stuff all over n to the 4th plus stuff. Okay, and nothing matters except the dominant term. And this is going to be n to the 4th. This is going to be n to the 4th plus 4n cubed plus, I don't care. It's just n to the 4th plus stuff. And therefore, this limit here is going to go to 1. And likewise, over here, you have n plus 1 squared, which is n squared plus 2n plus 1, but whatever, n squared plus stuff, all over n squared plus 1. That's also going to go to 1. And so it turns out, because of the fact that you only care about the dominant term, and when you look at n plus 1 over n, because that goes to 1, basically all of these limits are going to be 1. And there's nothing special about the polynomials that we picked. This is going to work for any polynomial function here. So if you have n squared plus 1 over n to the 4th plus 2n plus 3 all times -1 to the n, the ratio test is just not going to tell you anything because the limit turned out to be 1. What will tell you something is taking absolute values. So we're just going to have to do this one by hand. So if I look at the sum of the absolute values, -1 to the n times n squared plus 1, all over n to the 4th plus 2n plus 3, as n goes from 1 to infinity, or 0 to infinity, I guess. This is just the sum of n squared plus 1 over n to the 4th plus 2n plus 3, as n goes from 0 to infinity. And so here, if you look at n squared over n to the 4th, again, the only thing that's going to matter are the dominant terms, and this is going to behave like the sum of 1 over n squared, and therefore this is going to converge. And because the sum of the absolute values converges, this is what we mean by absolute convergence. So this converges absolutely. Okay, so notice that the ratio test failed, and indeed it'll fail for every rational function where you have a polynomial over a polynomial. But just doing it by hand worked very nicely. Okay, it was actually easier to do it by hand than to apply the ratio in the root test. Okay. Actually, we haven't talked about the root test, but let's get into that now. The root test is going to be very similar to the ratio test, and it's going to have basically the same motivation. And here the idea is, instead of looking at the limit of a sub n plus 1 over a sub n, what we're going to do is we're going to look at the limit of the nth root of the absolute value of a sub n. And again, here the motivation is, if I take the geometric series x to the n, and we look at the nth root, my pen's malfunctioning here, but I want to look at the nth root of the absolute value of x to the n, this is going to turn out to just be the absolute value of x, and we get convergence if the absolute value of x is less than 1. And so that's again going to be kind of our way to think about the root test, or if you ever forget what the root test says, that's one way to remember it. Okay, but let's write it formally. So let's let L be this limit. It turns out that if L is less than 1, then the series converges, so the sum a sub n, as n goes from 0 to infinity, or 1 to infinity, or 5 to infinity, whatever, converges absolutely. If L is bigger than 1, then the series diverges. And if L is equal to 1, just like the ratio test, the test is inconclusive. Turns out there are examples where the series can diverge, there's examples where the series can converge absolutely, and there's examples where the series converges conditionally. Okay? And so the root test is basically the same as the ratio test, except instead of looking at the limit of the ratios of the sequence, you're looking at the limits of the roots of the sequence, hence the names, of course. Okay? The root test is very handy when you have things like, let's think about, let's look at something like n squared plus 4 over 3n squared plus 7n plus 6 to the n as n goes from 1 to infinity. Now, if you were to try to do the ratio test, this limit would be a nightmare. You'd end up with essentially a bunch of terms that are going to have limits in here like 1 plus 1 over n to the n. I'm not going to write out the details here. The ratio test is definitely the wrong way to go. The reason why the root test is nicer is that we're taking the nth root of the terms. And so if there's an nth power, then those will just simplify. And so here, L from the root test is going to be the limit as n goes to infinity. And I forgot a -1 in there. Let's add a -1 to the n just to make it slightly interesting. But we're going to take the nth root of the absolute value of -1 to the n times n squared plus 4 over 3n squared plus 7n plus 6. And I forgot to put the nth powers there. Now, when we take the absolute value, what ends up happening is, of course, the power of -1 simplifies to just be 1. So this is the nth root of n squared plus 4 over 3n squared plus 7n plus 6 to the n. Okay, let me just move this stuff over a little bit so it looks nicer. That didn't work. Okay, so it's the nth root of that stuff to the n. And the whole point, the whole reason why the root test is nicer is that the nth root of nth powers simplifies to just give us n squared plus 4 over 3n squared plus 7n plus 6. And this limit is going to be 1/3, because again, the only thing that matters is the dominant term when you have rational functions. And that limit's 1/3, which is less than 1. That's all that matters. And so this original series, turns out, converges absolutely. Basically what the root test is saying, this root test is saying is that if we take the absolute value, so in other words, forget about the power of -1, this is behaving something like 1/3 to the n, which when n is large should make a good amount of sense, because n squared, just ignore the nth power there, but the inside, when n is large, the inside's about 1/3, and therefore this to the n is about 1 over 3 to the n. Okay, so it's like 1/3 to the n. So that's the root test. Okay, what I'm going to do next in the next video is just do kind of a few examples, and then I'm going to save most of the examples for us to talk about in class.